Good morning everyone, I'm Matteo Santilli from Roma Military University and I'm here today to talk you about our work, Distributed Finite-Time Algorithm for a class of quadratic optimization problems with time-varying linear constraints. The authors beside me are Professor Gabriele Oliva and Professor Andrea Gasparri. As many of you may know, in the last decades, distributed multi-agent systems gained a lot of interest in our community. One of the contexts to which have been applied a lot is the distributed optimization one. Many works in this context are currently focusing on time-varying problems, either it being for the time-varying nature of the interaction of the agents or either the time-varying nature of the constraints or the objective function of the problems. However, many of these works are either able to achieve asymptotic convergence to the optimal solution or only are able to guarantee a bound on the tracking error. In this work, we are actually able to provide a distributed algorithm that is able to track in finite time the optimal solution. The problem that we want to solve is the following. We want to find the optimal state x star that minimizes the function 1 over 2 squared norm of x, subject to a times x greater than the time-varying vector c, that is continuously differentiable. Notably, this problem satisfies at all times the Slater constraint qualifications. The working assumption of our work are the followings. We assume that the interaction of the agents are described by a connected and bidirectional communication graph G. We assume that the matrix A has the same structure of the graph G, and furthermore we assume that A is non-singular. And finally we assume that the constraint vector C is uniformly bounded, meaning that its derivative is actually upper bounded by a positive scalar k for all the time t. We will now derive some necessary sufficient condition for the optimality of the solution of our problem, and then based on such condition, we will design our distributed algorithm. The results are illustrated in Theorem 1. So, the frozen time problem at each time t has a unique global optimal solution in the form x star equal A transpose lambda star, where lambda star is defined as in equation 2. And to prove this result, we actually resort to the Cauchy-Tagger optimality condition, where we consider the Lagrangian function in 4, where lambda is the set of the Lagrangian multipliers. Then, utilizing the stationarity condition, we obtain the one in 5, that is the form of the x star. Then, from the dual feasibility, we know that each component of the Lagrangian vectors has to be greater than z or equal to 0. And then from the complementary Slacken condition and exploiting the fact that a matrix A is non-singular, the assumption 3, we are actually able to provide the optimal form of the ith component of the Lagrangian multiplier vector. That is illustrated in 7. Taking all the 7 for all the agents yields the stacked form 8. This actually proved our results. So, as I said earlier, we now want to design our distributed algorithm based on the track of this optimality condition. Before doing so, I want to introduce an intermediate result that we use later to prove the finite-time convergence of our algorithm. And it's the fact that the set of optimal Lagrangian multipliers is compact. And to show this result, we actually have to prove that the Mangasarian from its constraint qualification holds at x star, meaning that 9 has to hold. In our case, indeed it does, because the gradient with respect to the inequality constraint G is actually A transpose. And the fact that A is not singular allows us to derive a vector D of this form that satisfy the Mangasarian from its constraint qualification. And so the set of optimal Lagrangian multipliers is compact. To design the algorithm also, though, we prefer to rewrite the formulation in equivalent form, that is the one illustrated here in lemma 1, meaning that the optimal lambda star and x star that are described by the equation 11, so the theorem 1, are equivalent to finding a vector z star that stacks lambda and x such that the function w and g are equal to 0, where y is defined as such. With this in mind, we are actually now able to provide a distributed algorithm that each agent implements, where alpha is a positive gain, sine is the sine function, S is a diagonal matrix with entries y 1 or zeros depending on the value of the vector y. Note that this protocol requires two-hop state information because the agents require to know wj and gj. To obtain this information, we resort to a state-of-the-art finite-time observer that simply estimates those states using only one-hop information. In this case, we opted for the finite-time observer proposed by Gaspari and Marino. Furthermore, we also require, each agent requires the two-hop information on the values of the constants AJL, but since they are constants and not varying during the execution of the algorithm, we assume that they can be exchanged only once at the start of the protocol. Now, to provide the theoretical analysis, we will consider only, as I said, only for the theoretical analysis, the stacked form of the algorithm. That is illustrated in equation 16, where we consider a stacked vector H that collects W and G, and where the bold sign is actually the set, the vector sign, meaning that each component has the sign function of the argument, of the component of the argument, and where the M matrix is defined as in equation 17. Then also this matrix M will have to prove another result that will be used later. So let us introduce the set valued matrix Si, that is the diagonal matrix S equivalent, but where the elements corresponding to the fact that yi is equal to 0 can assume any value in the interval between 0 and 1. Considering such matrix S, we can define the set of matrix MS that depends on such S as M as an M. And we have that every matrix in this set, if we consider that A is also non-singular, are non-singular as well. The proof follows from the study of the Schur component of MS with respect to the right bottom block, that is minus identity. With this in mind, we can actually state our main results. That is the following. Consider a multi-agent system with dynamic 16, let assumption 1 to 4 to hold, and also assume that the gain alpha satisfies the following condition, where epsilon is a positive design parameter, sigma max is the maximum eigenvalue, and lambda sigma min, is the minimum eigenvalue. In this case of the family of matrices MS transpose MS for any MS belonging to M. And we recall that K is the bound of the derivative of the constant vector C. With this in mind, we can prove that there exists a capital T, a finite T, depending on the design parameter, that is such that after this T, problem 1 is solved. To prove these results, we consider the generalized Lag function presented in equation 21, which is norm 1 of the stacked vector H, which is actually positive for all the Z that are outside calligraphic Z set, and are equal to 0, that is equal to 0 for all the Z that are actually inside this calligraphic set. That is defined as the zeros of the function H, and it is compact, in virtue of what we discussed earlier. Now, resorting to Nozmud-Lyapunov theory from the works of Shevitz and Padden, we can compute a generalized time derivative as equation 23, where in this case, in our case, the generalized gradient assumes the following in 24, where the bold sign vector is actually the set valued sign vector. So when the component can assume values, could theoretically assume values equal to 0, instead it can take any value within the interval -1, 1, with both values included. Now, Considering the fact that our proposed control law is the Nozmud version of the gradient descent flow of a differentiable function, we can rewrite equation 23 as equation 25. We exploited the fact that the control law can be expressed as minus alpha partial with respect to z of the Lyapunov function. With this in mind, and considering also the fact that partial zv is a convex set, we can obtain the following equation, the following bound, considering all the z outside the calligraphic set z, and we exploiting then the structure of an element of a generic element of the partial of generalized partial gradient. We can that is the following, where z is composed of two elements, where eta belongs to the bold set valued sign function, and mzs is a matrix that depends on S, and the mts is a vector that depends on S. We can actually derive the following bound on the generalized time derivative, and exploiting then the structure, the assumption that we made on the gain alpha, we could actually prove that this is bounded by that is less than 0. Is actually upper bounded by minus epsilon, when epsilon, I recall, that is our design parameter. Then we have that V reaches the origin finite time and Z reaches the compact set calligraphic Z in finite time as well. As a consequence, we have the optimality conditions are met, and problem 1 is then solved for all t greater than this capital T that depends on our design parameter. Finally, to corroborate our theoretical findings, we consider a multi-agent system with 10 agents, and where the constraint vector evolved as in figure, and we can notice that its derivative is bounded. And we can show that after some certain finite time around 3, both the V and both the tracking error reaches the origin and remain 0 for all the rest of the simulation. To conclude, what we provide to you today is necessary sufficient optimality condition for a class of quadratic optimization problem with time varying constraints, and based then on such condition, we actually propose a distributed algorithm that is able to track in finite time the optimal solution. We are now working on a manuscript that generalizes the objecting function and also design an adaptive tuning gain that removes any the need for any prior knowledge on the system for the gain alpha. And that is all. If you have any question, feel free to email us at the following address or write it down in the chat. Thank you for your time.